check this out. We've got something really fun today. This is so amazing, math. Oh man, again? Let's warm up. Let's rewrite these expressions in a different form using our exponent rules. So this one is 5 to the power of x minus 2, and we know if we're subtracting in the exponent, that is like dividing by that exponent with its own base. And we can do the reverse. If we have this, we can say this is x, and the exponent will be 5 minus 3. And so a different way to write this one is just x squared. 1.3 geometric sequences. We want to determine the pattern for the following sequence. Look at it carefully, see if you can figure it out. Notice that each one of these is being multiplied by 3. And it's more obvious at the beginning when the numbers are smaller, but the pattern does continue and you can check that out. Now, a geometric sequence is a list of numbers in which the ratio of consecutive terms is constant. In other words, if we divide a term by the preceding term, it will always give the same number. So this is our notation. R is going to be our common ratio, and Tn divided by Tn minus 1 is how we get that ratio. We want to derive the general term for geometric sequences, Tn. Now let's start off with just T1, T2, T3, T4, and so on, all the way to Tn. And we're going to derive this just by observing the pattern. So T1 is just T1. T2, though, can be written as T1 times this R value. And then T3 can be written as T2 times R again, or T2 can be written like this. So it's T1 times R times R. This one, T1 times R squared times R again. This right here is T3 times R again to get to T4. This is T4 times R again to get to T5, and so on. And you notice that this exponent here is always 2 behind the term number. So 5 minus 3 is 2, 4 minus 2 is 2, and 3 minus 1, and so on. So when we get to here, it's n minus 2 for this exponent, and then times r to get here. Now we'll multiply in these r's. We're just using those to find the pattern. So this one is 0 r's. This one has 1 r, 2 r, 3 r's, 4 r's, and so on. And you notice the pattern. It's always, this exponent for r is always 1 less than the term number. So this one is 1 less, so it's 0. 1 less is 1. 1 less is 2, and so on. So when we get up here, it's 1 less than whatever n is. And that is our general term. We start off with T1 and multiply by the common ratio n minus 1 times to get to Tn. Let's look at the sequence 2, 6, 18, 54, 162, and so on. Determine the value of T16. So to find T16, it's probably useful to find our general term, Tn. Now that would be T1 times r to the n minus 1. Let's fill in the things that we know. Tn is what our general term is. T1 is 2. Our r we need to find. We can find it by dividing any two of these. So 6 divided by 2 we find is 3. Or we could have done 18 divided by 6, that's also 3. Or we could have done 54 divided by 18, that's also 3. Or any one of these will work. So our common ratio is 3. So this is our general term here. Now let's find T16. So T16 is equal to 2 times 3, 16 minus 1. And this, when you put it in your calculator, it equals 28,697,814. Now, just a reminder, I see a lot of students messing up on this type of thing. If I have 2 times 3 to the power of 15, I cannot, absolutely not, multiply the 2 and the 3. They can't go together. Remember, in our BEDMAS rules that we've established, we must do the exponent here. So I can't get this 2 with the 3 because it has its own exponent that I need to deal with first. Example 2, if T1 is 4 and R is 1/2, determine the general term formula. And then using a calculator, I'm going to sketch a graph of Tn. And is the graph linear? First, let's get our general term. So Tn is equal to T1 times R to the power of n minus 1. Now there is something we could do here, and that's simplify this. So I could say this is 4 and this is 0.5 to the power of n, and this, like we did in our warm-up, is 0.5 to the power of 1 here, because it's minus 1, so that would be like dividing by 0.5 to the power of 1. And now I can go 4 divided by 0.5, and I can get 8 here. Now this is perfectly fine as we wrote it at the beginning here. It's in our general term form that we commonly use, but this is also possible, so keep this in mind as you're doing these questions. Now let's graph this, and when we do, we see that it looks something like this. Now I know that I'm going to graph it on my calculator, so it will be continuous, but I know that this is not continuous. It's just a bunch of dots on the graph, discrete, okay? But this, when you put in your calculator, it looks like this, and we just want the shape of it to answer this question. Is the graph linear? Well, no, absolutely not, because it's got this curve to it. It's actually exponential. In this question, we're given T1 and T5, but we're not given R, and we're not given 2 terms that are beside each other, or 2 consecutive terms that we can easily divide to get R. That's okay, we can still use our formula to figure out what R is. Let's set it up. We could say that T5 is equal to T1 times R to the power of 5 minus 1. Let's put in the numbers that we know. So T5 is 3. T1 is 1 over 27, and we got R to the power of 4. Now multiply both sides by 27, and we get 81 is equal to R to the power of 4, and we're going to take the 4th root of both sides to get rid of that power of 4, and we get that R is equal to, because this is an even exponent, it could have been positive or negative in here, we don't know. So R could be plus or minus 3. So it looks like we have 2 different cases that we'll have to check out here. So let's find T2, T3, and T4. Now if our T1 is equal to 1 over 27, and our T2 then, the first one we'll say is R is equal to 3. So our T2 would be 1 over 9, our T3, 1 over 3, and our T4 would be 1, and that makes sense because our T5 would be then 3. Let's try out this other option though of negative 3. So if R is negative 3, then our T1 is still 1 over 27 because that's given in the question. But this time let's multiply by negative 3, we get negative 1 over 9. Let's multiply negative 3 again, and we get 1 over 3. So these actually match again. These match. So it looks like all the odd numbered terms are going to match. Multiply by negative 3 again, we get negative 1. Multiply by negative 1 again, we get 3. So either one of these answers works with the information we've been given in this question. In a geometric sequence, T2 is negative 6 and T7 is 192. First thing we want to do is find the common ratio. Now it might be obvious to use a system of equations. So let's do that way first, even though it might be a bit longer. It might be more obvious to some students. So we could say that t2 is equal to t1 r to the power of 2 minus 1. And we can put in the numbers that we know here. So this is negative 6, and this is t1, which we don't know, and we also don't know r, and this can be simplified to just 1. Now the other equation we can make is with the t7. So t7 is equal to t1 times r to the power of 7 minus 1. And we can adjust this to, this is 192 is equal to t1 times r to the power of 6. Now you notice that we have a t1 here and a t1 here, so it might be easiest to use substitution, solve for t1 in both these equations, and set them equal. So this one I'm going to bring up here, and this one up here. So t1 is equal to negative 6 divided by r, and this t1 is equal to 192 divided by r to the power of 6. And now I'm going to set them equal to each other because they're both equal to t1. So we get negative 6 over r is equal to 192 over r to the power of 6. Now I'll multiply by r to the power of 6 over here, and that will bring me r to the power of 6 divided by r, and then I'll divide by negative 6 on both sides. So that will give me negative 32 on this side. Now this is really just r to the power of 5 equals negative 32. So taking the fifth root of both sides here, I get r is equal to negative 2. Now that's using a system, and let's try just adjusting the formula. Now just like we adjusted the formula for arithmetic sequences, we can do the same for geometric sequences. So this starts at 1 and this is minus 1, but there's really no need to do that. We could have Tn is equal to Tm r to the power of n minus m, because to get from this term m, whatever it is, you can multiply by r n minus m times. So now we can just use t7 here and t2 here. So in our case, this will be t7 is equal to t2 r to the 7 minus 2 times. And hopefully it's more clear once we put the numbers in. From t2, we need to multiply by r 5 times to get to term 7. Now let's put in the numbers, and this one is a bit better because we didn't have to solve for two equations here, the system. So 192 is equal to negative 6 times r to the power of 5. Divide both sides by negative 6, we get negative 32 equals r to the power of 5, and you can see we've jumped in right here. So take the fifth root of both sides and you get r is equal to negative 2. So obviously if you can remember this adjusted formula, it will be a bit easier. Let's do the first term. So the first term is equal to, how about the second term divided by r? So the second term is negative 6 and r is negative 2. That means the first term is 3. Now let's do the first 4 terms. So if t1, t2, t3, t4, t1 is already 3, and then just multiply by negative 2 each time. So negative 6 and 12 and negative 24. The first term in a geometric sequence is 2, and the common ratio is also 2. The value of the last term is 1024, so how many terms are there? Let's set up our equation. Tn is equal to T1 times r to the power of n minus 1. Now we know that our last term here is 1024, and our first term is 2. Our common ratio is also 2, so we can put that in, but we don't know n, which is our last term, or the number of terms in this sequence. Now I can put the 2 and this 2 together. Remember, this 2 would have an exponent of 1 here, We don't need to write it, but maybe it's helpful to see. When we put these together, they have their own base, so we're going to add the exponents. So 1 plus n minus 1 is just going to be 2 to the power of n. And now we need to solve this, but the difficulty is that n is in the exponent. So the way we solve this is we can either graph this and get a solution on our calculator, or we can rewrite it using the same base. So 10,024 actually can be written as 2 to the power of 10. Now once we rewrite it like that, we can see that they have the same base, therefore the exponents must be equal. So n is equal to 10, so there's 10 terms in this sequence. Janice is enlarging an image using computer software. The length of the image is 150 pixels, and the enlargement she makes is 110% of the original. What is the length of the image after 4 enlargements? So let's set this up. Here's, say, her image at first, and it's got a length of 150 pixels, and this will be our first term. Now she's going to enlarge it so that it's a bit bigger, and that's the first enlargement. She's going to make 4 enlargements, so that's 1, 2, 3, and 4. So there's our 4 enlargements, and each time they are 110% of the previous. And obviously I'm not drawing this to scale, but just to give you an idea. Now if this was term 1, then we'd actually be looking for term 5, because that will give us 1, 2, 3, 4 enlargements to get to term 5. So here's our equation. Tn is equal to T1 r to the power of n minus 1. We're looking for T5, and our original T1 is 150 here. Our ratio is 110%, so I need to write that as a decimal, so it's 1.1, and then to the exponent 5 minus 1. Now we can just put this in our calculator, so we get the fifth term is 220 pixels. Example 7 is pretty interesting. We've got 2m minus 2, 2m plus 2, and 5m plus 1 are the first 3 terms of a geometric sequence. Determine the value of m and the value of each term. So this one, it's not entirely obvious what we're multiplying, even though we're given 3 consecutive terms. So our r is equal to, say, T2 divided by T1. That would be 2m plus 2 divided by 2m minus 2. Now, I can't do anything with that, so what else can we do here? R also equals T3 divided by T2. So this would be 5m plus 1 divided by 2m plus 2. And what should I do with that? So I've got 2 r's here, so they're actually equal. So let's set them equal. 2m plus 2 divided by 2m minus 2 is equal to 5m plus 1 divided by 2m plus 2. Now let's multiply both sides by 2m plus 2 so that it moves up here, and multiply both sides by 2m minus 2 so this moves up there. So this one will be 2m plus 2 times 2m plus 2, and this is 5m plus 1 times 2m minus 2. Now I'll multiply in these binomials, so 4m squared plus 8m plus 4 equals 10m squared minus 8m minus 2. Now let's move everything to this side so I can have a positive leading coefficient. So get 0 is equal to 6m squared minus 8, so minus another 8 is minus 16m, minus 4 minus 2 is minus 6. Now, looks like I have a common factor here. So first thing I'm going to do is just simplify this quadratic by dividing everything by 2. So 0 is equal to 3m squared minus 8m minus 3. And that quadratic is hopefully easier to work with. Now let's see if we can factor this. So we got 3m and an m here. And a 3 is going to go here, minus and plus 1. So it does factor. And let's see what our m would be then. Got negative 1/3 from this binomial and 3 from this binomial. That means that there's two sets of solutions here because we get two different values for m. So let's write this out. M equals 1/3. Then we want to find t1, t2, and t3 when that is negative 1/3. Now let's do it again when m is 3. We'll find t1, t2, and t3. Okay, so t1, if you look back up here, t1 was equal to 2m minus 2. And if m is negative 1/3, and we put that in here, then we get negative 8 over 3. We get 4 over 3 and negative 2 over 3. And when m is equal to 3, it's a lot easier. Put in a 3 into t1, put a 3 into t2. We get that t1 would be 4, t2 would be 8, and t3 would be 16. So here's our two sets of solutions for this question. This was part of Relations and Functions 10, analyzing geometric sequences. Here's some questions from the textbook. Give them a try. See if you know what you are doing.